In this lesson, we're going to have 4 more organic families and figure out how to name those as well. So we've got alcohols, aldehydes, ketones, and carboxylic acids. So just a reminder, although it's come up a few times, that a functional group is any group of atoms or singular atom or type of bond that is going to make us have a different organic family because of the properties that it's going to present from that functional group. So we've seen double and triple bonds, we've seen halogens, we've seen a benzene ring, and we're going to see a few new functional groups in this presentation that give us 4 new chemical families. So here are those functional groups. We can have either of these guys. So the R, obviously we haven't seen an element come up that's letter R yet. The R just means the main chain. So this is where the carbons are. So we've got carbons attached to an OH group. OH group is called a hydroxyl, and we've already seen that. The hydroxyl was attached to a benzene ring in our last lesson, and that's when we called it a phenol, right? So we'll see more things with OH, a hydroxyl. If we've got a carbon with a double bond to an oxygen, this is called a carbonyl group. And we'll see it in a few different ways. So again, we can have it attached to some more carbon chain, possibly on both sides. And then we can kind of have like a fusion of both of these groups together. So we've got the OH group coming off a carbon, we've got the double bond coming off the same carbon. When that happens, this third functional group is called a carboxyl. So it's kind of both of those other functional groups tied together. So 3 different functional groups. The way they fit into a molecule is going to give us 4 different families. So this is just a summary page. We'll break it down into each different family in a moment. We can see that alcohol has that OH group, has a hydroxyl. Here's an actual example without that R, and we're going to be using a new suffix. So if we see anything that ends in OL, we know we're dealing with an alcohol. We know there's a hydroxyl present. So phenol ended with an OL has that OH present. Aldehydes have a carbonyl, and it's going to end in AL. Like aldehyde, al is going to be the ending. So here's a real one. We've got that carbonyl right there. Aldehydes and ketones look very, very similar because a ketone also has a carbonyl. The main difference, though, is where that carbonyl is going to be within the chain. So ketone ends in -one for the suffix. And we'll look more at where these carbonyl groups are within the chain as we get through this lesson. Lastly, carboxylic acids have both of those functional groups, has the carboxyl, the double bonded oxygen, and the OH all coming off the same carbon. And it has the suffix oic acid. So let's look a little bit closer at each of these. And do a little bit of naming. So alcohols, the first one in our chart, has that hydroxyl group, has an OH, and alcohol, OL, is going to have the suffix OL. And when we were looking at other functional groups, like double bonds and triple bonds, they had to be in the main chain, right? So it's no different for this kind of stuff. That OH has to be in the main chain, even if you could build or find a longer main chain. So there are different types of alcohol based on how many carbons are bonded to the carbon attached to the OH. So they're called either primary, secondary, or tertiary. So this carbon is the one attached to this OH group, and it is also attached to one other carbon. One makes it primary. This one's a little bit easier to see because it's in a structural format. So this carbon is obviously attached to that OH. It's attached to two other carbons. Two other carbons makes it secondary. And if the carbon that's attached to the hydroxyl is completely filling its bonds with other carbons, 1, 2, 3, it's tertiary. So this is the exact same slide. I've just kind of numbered it out in case you go back to the presentation on your own. And this won't change how you name them at all. It just causes alcohols to react in a different way, depending if they're primary, secondary, or tertiary. So for the aspect of naming in this presentation, this kind of idea of primary, secondary, and tertiary isn't going to really play any impact for us. So let's look at a couple of names, just full well remembering that the OH needs to be as low as possible, just like our double and triple bonds. So this guy's already numbered out for us. We've kind of cheated. I'm sure because it looks smaller and we've seen a bunch of different, more difficult stuff, you'd probably hone in quickly and say, oh, this is my main chain right across. Or if you like to make things difficult on yourself, maybe you labeled this as 1, 2, 3, 4 and left this CH3 as the methyl group, maybe. Anyways, so just to make sure we're labeling from right to left, just because we want this OH group to be as low as possible. It's just super cool that it also makes this methyl group as low as possible. So one of the typical mistakes people make is when they see an OH group, for some reason they always want to make that carbon number 1. Just remember to still try to make the longest main chain you can, just that main chain has to include the OH, and then we try to make it the lowest number possible. So OH can be numbered, that's where that 2 comes from. It doesn't have to be number 1, just as low of a number as possible. So anyways, we have a 2-methyl coming off of there, and that 2 is here because that's our location of our OH group, which makes it an alcohol, just like we were doing when we had double and triple bonds. And it's a butane because there are 4 carbons all singly bond. That's why we keep that AN, to show that there's no double or triple bond. We could also have, just like how we had an OH on a benzene ring, we could have an OH on a cyclic. So it's a square, 4 points. That's also going to be a bute because there's 4 corners, 4 carbons, and cyclo because we've got a shape. So we have a cyclobutanol. We can call it a 1-cyclobutanol if we really want to, kind of like when we had double bonds, just to show that we are numbering correctly or fearful of forgetting to number other times. But not necessary because we would just presume that we see an OL, there must be an OH group in here, and no matter where we were to draw it, it would be on carbon number 1. Okay, so let's do one without an answer directly on the page. So we've got a long chain going right across the middle, right? With an OH group popping off, a CH3, and a chlorine. So if we didn't already know this was an alcohol, we would be like, ooh, OH group. That's what's making it an alcohol. I'm going to make sure when I write out my entire name, I'm going to end it with the suffix OL. So this part is the functional group. We want to make that functional group as low as possible, so that when I'm numbering my main chain, I'm going to number this carbon as carbon 1, so that this carbon with our functional group is number 2 and is as low as possible. 3, 4, 5, 6. We've got a hexanol. We keep the AN to show that there are all single bonds, and then the OL showing us that there is an OH. On carbon 4, we have a chloro and a methyl. Let's go to the next slide just so we can see it all. So carbon 4, we've got the chloro, we've got the methyl. Carbon 2, we have the stuff that makes it an OL. We've numbered in the direction that makes our functional group as low as possible. Now we just have to glue everything together in alphabetical order. So chloro comes first because it's a C, the 4-chloro before the 4-methyl. Then we have to say the location of where this OH group actually is before calling it a hexanol for being 6-carbon chain, all single bonds, so we keep the AN, and then OL for the alcohol, the fact that there's an OH there. So those are alcohols. The next group we had in our chart were aldehydes. So instead of having an OH group, we now have that C double bond O, carbon doubly bonded to an oxygen. Aldehydes will now end in AL. So sometimes when I'm speaking it sounds a lot like OL, but I'm going to try to overly pronounce my ALs. Excuse me. And one specific thing about aldehydes, because remember we had aldehydes and ketones, both containing a carbonyl group. The specific thing about aldehydes is that carbonyl group has to be on carbon number 1, which is kind of nice because if it is on carbon 1 always, it also means we don't actually have to number it. So it's a little bit nice. So a couple of aldehydes for us. This is the simplest aldehyde we could have. It's 1 carbon. So obviously that double bonded oxygen is on carbon number 1. And we would give it a meth because that's obviously what we've been using so far for a single carbon. Keep the AN because there's no carbon-carbon double bonds. This double bond doesn't count. It's not to 2 different carbons. And then our suffix AL saying that this is an aldehyde. This one's a bit harder. We see a carbon on the end with a double bonded oxygen. And so we'll say, hey, this is an aldehyde. This must also be carbon number 1. I already know which way I want to start numbering my chain to make it 1, 2, 3 methyl, 4, 5 carbons long. So it's a pent. Everything's a single bond. And then we put AL on the back of it because it is an aldehyde. Okay, so let's see one without the answers. We look at our, whoopsie, double whoops, oh my goodness. So we look at our molecule and we see a double bonded oxygen. And then we notice that there's no more carbons coming off this side. This must be carbon number 1. So if this is 1, 2, 3, 4, we have a bute. They're all single bonds, and al because of this aldehyde. So that's a butanal. We also have something sticking off of it, right? On carbon number 4. NH2 doesn't pop up too often for us, but that's an amino. So we have a 4-amino butanal. So it's a little bit harder when we get into worksheets where everything's mixed up, but make sure you're looking for those functional groups and trying to maybe as the first step saying, okay, what organic family do I have? What is my suffix going to be? So looking for that OH, looking for that double bonded oxygen, just to know how you want to kind of name as you get through each question. So ketones, those are the ones that are a lot like aldehydes. So obviously also have that carbonyl. We're going to change the suffix because we've got a new organic family now. Ketone is going to have an -one suffix. The big difference is pretty much that carbonyl group is going to pop up anywhere within our chain, just not carbon number 1. So it's going to be somewhere in the middle, in the center. So let's see. We've got obviously the ends of our chain on either side, and that carbonyl is popping up somewhere in the middle. Here are the ends. If there was a double bonded oxygen over here, that would make it an aldehyde, but it's falling in the middle, which makes it a ketone. Same thing here. So these are all ketones instead of aldehydes, just because that carbonyl group is within the chain. So let's take a look at the names. Obviously they're all ending in -one because we've got ketones. Butanone doesn't even have a number though. So that's because this is on carbon 1, 2, right? We've got it a 2-butanone, 3, 4. We can't have a ketone be a 1-butanone. It wouldn't exist. It would be a butanal if it were over there, right? Because we'd now have an aldehyde. So it can't be on this side, can't be on that side. If it were on this carbon instead, well, we still want to make sure that carbonyl is labeled as the lowest number possible. So we would now label from this end of the chain, making it a 1, 2 butanone still. So there are some times that you don't have to put numbers based on that. So this isn't a typo of mine. You by all means could write 2-butanone. However, a 3-butanone would be a wrong answer just because we're not labeling in a direction that gives us the lowest number possible. When we get to a 5-carbon chain though, both of these are 5-carbon chains, we need numbers because now we could have them in 2 separate places. We could have a 2-pentanone, or it could be 1 carbon in and give us a 3-pentanone. However, there's no such thing as a 4-pentanone because then we would just number in the opposing direction and make sure that we get a 2-pentanone. So those are ketones. We've got one left to go through, and those would be carboxylic acids. So these ones look like they're the hardest just because they've got both those functional groups together. So the hydroxyl we saw on alcohols, and the carbonyl group we just saw on aldehydes and ketones are going to be together on the same carbon, and we'll have a carboxylic group. So our suffix now is oic acid, which is nice. We finally get to use a space, even though it's just the word acid. And we'll see on the next page different ways that we can show a carboxylic acid. So these are 3 different ways you might see on worksheets or online if you're searching for stuff of how to actually draw things out. So the way most people like to see it would be kind of in a structural format. So seeing all the bonds. So you can see that this carbon has a double bonded oxygen and also that OH group. So there's our carboxyl, and it might be attached to some more stuff. So this is ethanoic acid because we've got 2 carbons. AN sticks around because they're singly bonded, and oic acid tells us that we've got a carboxylic acid. So ethanoic acid is acetic acid, which is vinegar, probably if you've seen the label before, if it sounds familiar. So our carboxylic acid piece, that carboxyl, is always going to be carbon 1. So I didn't have to label anything with numbers. Here's another one I found online, and I put a big X in it because I don't want you to do it because it honestly doesn't show where the double bonded oxygen is. It just shows a single bond, which just isn't right. So you might see it that way depending where you're looking. If you're doing some extra research, just make sure if you were to ever to draw it to make sure that double bond still exists to show that we've got a carbonyl here. And we've already seen this method when we looked at benzoic acid, and we've just got a condensed diagram without showing all the bonds, and it's a COOH. So this is showing us our carboxyl group here, making sure that this C is carbon 1. We've got some extra stuff hanging off of here. 1, 2, 3, that's where our 3 ethyl came in, and we must have 6 carbons long to make it a hex. All single bonds, AN sticks around, and oic acid tells us that we're dealing with a carboxylic acid. So let's look at something hard before we finish the lesson. So name this guy. We've got it kind of showing us the structural, but then we've compressed this COOH all together. So here's our carboxyl. The C right attached to it has to be carbon 1. So we would have carbon 1, 2, 3, 4. Our main chain would be some sort of bute, 4 carbons long with a methyl group, but we also have this double bond. So we have to figure out how to name that into it. So I've always made reference that we said we had butan, and the an came in because it's all single bonds, oic acid, to show it's a carboxylic acid. Well, now we're going to have to change that bute to an N, En, oic acid, to signify that there's a double bond. We'll also have to throw in a number to show the location. And we'll also have to kind of glue to the front the fact that we have a methyl group on carbon number 2. So let's see that kind of written out so it's a little bit easier. So all this functional group stuff tells us we have a carboxylic acid. We know we're going to be ending our molecule's name with oic acid. We're going to find our longest main chain. It's 4 carbons long, and we know we have to label it as number 1 here because that's where we want to make our functional group as low as possible, and we can't get lower than 1. And at least we can pretty easily say, hey, that's a methyl. We have a double bond here too, so any other time we've seen that, we know we want to change our suffix to -ene, but we already have an oic acid suffix, so we're going to have to throw that in elsewhere. So the way we put that in is instead of saying butanoic acid, we would change it to butenoic acid. So we can see that we have the double bond here and put the number as to where it came from, the number 2, the lowest number, to show, hey, this is where it actually is within the chain, because maybe it could have been over here, right? Or over here. So we want to make sure we label where that actually popped up. And then perhaps the easiest part, but might forget it after doing all of this hard work, would be to remember to say, hey, and we also have this little methyl group popping off the number 2. So if we fused it all together, we have a 2-methyl, 2 for the double bond, 2-butanoic acid because of the carboxylic acid hanging off the end.